When you are asked to do calculations with bond energies, they are often or almost always given in the form of a table. For the sake of space and trying to keep the paper condensed here, I just have them across the line here listed as the bond energy of a carbon to hydrogen, a carbon to carbon double bond, a hydrogen to fluorine, a carbon to fluorine, and a fluorine to fluorine bond. Sometimes you're given way more bonds than you need. Sometimes you're only given the bonds that you need. And we'll practice with some things in class and in labs and online that there are instances in which not every bond is broken or formed, and we can account for that as well. But we're thinking about not just all of the bonds of the reactants, but the bonds that must be broken to turn from reactants to products. Not necessarily all the bonds that are formed, but the bonds that are formed as we put our separate things back together into products. Having a sketch or a Lewis structure is super helpful for this, but not necessarily required. We would take the information that we're given and try to figure out what is pieced together. Well, in this, we do have a carbon bonded to a carbon, and we have 4 hydrogens, each of which is attached to a carbon. Although that may not be obvious from the formula, if we drew that out, we could know that for sure. With F2, we have an F bonded to an F right there, and because of the coefficient of a 6, we know that we have 6 of those. Within 2 CF4s, that means that each C is bonded to 4 Fs, or I have 4 CF bonds, and I have 2 sets of that, or 8 C to F bonds. With the 4 HFs, I have 4 H to F bonds. So it is very valuable to take the time to write this step out, to keep track and to add up all of your bonds. And if you haven't already been asked to do drawings of the structure, it's usually worth the time to do a quick sketch so that you can count how many bonds are broken and formed. Then you plug in the numbers. You make sure that you're doing broken minus formed. You've got your subtraction sign in there. You add everything up, and we get a negative 2,567 kilojoules. So it's an exothermic process. We could also make the connection here that although not asked in the problem, we could think about our activation energy, and it does ask for a sketch of the energy diagram, which I didn't do, but it would look something like this. Our uphill would be 3,221, so that's how much that would be, our 3221. And our downhill, that entire thing there would be the 5788, which would leave right there as my negative 2567. So super ugly, but you get the idea that I know exactly how much up, exactly how much down, and exactly how much the difference is as well. The next one is asking about a specific bond energy. So we know whether whatever information we're given, that it's bond broken minus bond forms equals delta H, and they tell us that this is an exothermic process with a delta H of negative 81 kilojoules. So we can plug in our negative 81, we can plug in the things that we know, and we need to be very careful to note that there are 2 H to I bonds as we are solving this. So when we combine these together to come up with the value, something in that 587 range, we subtract it over to this side. We're even higher than that. We're in the 600 something range, which is why each bond has a bond energy of 334. Earlier, we were thinking very much of positive, negative as endo and exo, but bond energies are always a positive value. So we don't want any negatives there, and it should just connect with what we know as well. Then the last question here is that methane burning is exothermic. What do we know about the bond energies? Well, delta H is broken minus formed. The enthalpy change is negative, so the formed must be greater. This is a very common, very straightforward, but very easy to miss AP style question on this. It's very I said vary a lot. I get that. It's simple to write the equation and just think about if this is positive or negative, what has to be greater than the other. Without the equation, that becomes a little bit trickier. So it is important to write the equation and go through that process, remembering broken minus formed.